guys, these are notes for the first half of section 42.3, which starts on page 627 of your book. So the first thing that they will talk about in Springboard in section 42.3 is the fundamental counting principle, which basically says if one event can occur in m different ways, and a second event can occur in n different ways, then together the event can occur in m times n different ways. So for example, if you have 4 shirts, 3 pairs of pants, and 2 jackets, how many outfits can you make? Okay, so we've used this before without calling it the fundamental counting principle. But you have 4 choices for your shirt times 3 choices for your pair of pants and 2 choices for your jacket, so you get 24 outfits total. Now, there is a notation that we're going to see in factorial, and n factorial, put this in parentheses for you, it's n with an exclamation point next to it, and anytime you see that, it means the product of n times n minus 1 times n minus 2, and you keep going all the way down to times 3 times 2 times 1. So, for example, if I wanted 5 factorial, that's the same as 5 times 4 times 3 times 2 times 1. And so 5 factorial would be equal to 120. If I wanted 7 factorial, that's the same as 7 times 6 times 5 times 4 times 3 times 2 times 1. If I put that in my calculator, it's the same as 5,040. Sometimes they'll ask you to solve a problem that looks like this one, where it says 10 factorial over 5 factorial times 2 factorial. So if I were going to solve that problem, I would start by writing out, okay, 10 factorial, I know that's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But I stopped right here at 5 factorial. I wrote it as 10 times 9 times 8 times 7 times 6 times 5 factorial. The reason I did that is because if you'll notice, I also have a 5 factorial in the denominator, so I can cancel those two. So in my numerator, I would end up with 10 times 9 times 8 times 7 times 6, and after I canceled the two 5 factorials in the denominator, I would end up with 2 factorial. 2 factorial is 2 times 1. So my calculator, if I take 10 times 9 times 8 times 7 times 6, and I divide it by 2 times 1 or 2, I get 15,120. Okay. So now we're going to learn to use this. We will use n factorial when you solve permutations. So a permutation P is an ordered arrangement of a set of objects. So one of the things that you need to make sure that you look at is it's an ordered arrangement of a set of objects. So for a permutation, order is important. So my first example is how many ways can you arrange the letters in the word math? So if I'm going to do this, I have 4 letters in the word math. So if I want to arrange the letters, so I have 4 choices for the first letter. I have 3 choices for the second letter. Then I have 2 choices for the third letter, and 1 choice for the last letter. So that would be 4 times 3 times 2 times 1, which is 24 arrangements. So what an arrangement means is, so M-A-T-H would be one arrangement of the letters of the word math. But then I could have done M-T-H-A. That would be another arrangement. Or M-T-A-H. That would be a third one. Or M-H-A-T would be a fourth one. Or M-H-T-A. So I could write down, if I arranged all the letters in the word math, there would be 24 possible arrangements. So then I could have T-H-A-M. So there's 24 possible arrangements of the letters of the word math. So an arrangement means how many ways can I rearrange the letters in this word? So 24 different ways. If you'll notice, 4 times 3 times 2 times 1 is the same as 4 factorial. Now I didn't write out all 24, but there are 24 different arrangements of the letters in this word. So our next example, we have 5 children that line up for a family portrait. How many different ways can the children line up for a portrait? So here's 1, 2, 3, 4, 5. I have 5 spaces for these 5 children. So in the first, if I'm the photographer, I can pick any one of the 5 children to begin with to stand in the first place. So I have 5 choices. But then in the second place, I picked one of the children, so I only have 4 choices, 4 children left. In the third place, I would only have 3 children left to select from. In the fourth place, I would only have 2 children to select from. And finally, I would have 1 child left. So if I want to know how many different ways can the children line up for a portrait, that would be 5 times 4 times 3 times 2 times 1, which is the same as 5 factorial. And if I put that in my calculator, it is 120. Now let's say, so let me give you some notation for that. So if you have permutation, you will see this oftentimes. So this is the same as N. This big P is going to stand for permutation. So whenever you see this big P, capital P, that means permutation. N, P, N. So N permute N. So that means I'm taking all N objects and I'm arranging them. So anytime I have N objects and I want to arrange them, that formula is going to be N factorial. So if you notice in the last 2 problems that we've done, want to rearrange the letters of the word math, it was 4 times 3 times 2 times 1, 4 factorial or 24. I'm taking N objects and I'm rearranging all N of them. Now, we're rearranging all of them. So I took 5 children and I want to know how many ways can those 5 children line up for a portrait. Now let's look at this problem here. Suppose only 3 of these children can be seated on a bench. How many ways can 3 of the 5 children be seated on a bench? So this problem is a little bit different. I'm only taking 3 of the 5 children. So if I wanted to figure out how many ways can 3 of these 5 children be seated on a bench, well, for the first seat on the bench, I would have 5 choices because I still have 5 children. For the second seat on the bench, I would have 4 choices. And for the third seat on the bench, I would have 3 choices. So I would have 5 times 4 times 3 choices total, which is 60 different ways to seat the children, 3 of the 5 children on the bench. So there is a formula that says the number of permutations P of n distinct objects taken r at a time is given by the formula n permute r equals n factorial over n minus r factorial. So if you were to look at this problem, in this problem, I have really 5 children. I am taking 3 of them to put on a bench. So that's going to be equal to okay, 5 factorial over, and you notice it's n minus r, so 5 minus 3, which is 2 factorial. So if I were solving that out, I would solve it out like this. I would say, okay, 5 factorial is 5 times 4 times 3 times 2 times 1, or times 2 factorial. And on the bottom, I have 2 factorial. The 2's will cancel, and that will be equal to 5 times 4 times 3, which is just equal to 60. So this formula means you have 5 total, and you're taking 3 at a time. So that's the number of permutations of 5 taken 3 at a time. So if you have 5 and you took all 5 at a time, which is the first problem, n permute n is n factorial. So if you arrange every single object that you have, it's always going to be n factorial. So in this case, it was 5 times 4 times 3 times 2 times 1. If I arrange all the letters in the word math, it was 4 times 3 times 2 times 1, or n factorial. So the last two examples I want to show you, this next example is a little bit different. It says, how many ways can you arrange the letters in the word Tallahassee? So if I were looking at this, like I did the other problems, I would say, okay, I have 11 choices for the first letter in the word Tallahassee, because if I count, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters in that word. And 10 choices for the second letter, and 9 choices for the third letter, and 8 choices for the fourth, and so on, just like I did before. The problem is that some of the letters in the word Tallahassee repeat. So you have more than one A, and you have more than one L, and you have more than one S, and you have more than one E. So in that case, when you rearrange those letters, you don't really have, like you have 11 choices for the first letter, but then when you get to the next choice, you have to divide some of these permutations out. Because, you know, if you have an A in the 10th place and an A in the 8th place, so you put the first A in the 10th place, for example, the second A in the 8th place, that's going to be the same as if you put the second A in the 10th place and the first A in the 8th place. So what I mean by that is if you have things that are repeated, you have to divide something out. So the number of permutations P of n elements taken n at a time, you're looking at all of them, with R1 like elements of one kind and R2 like elements of another kind, and so on, is given by this formula. P equals n factorial over R1 factorial times R2 factorial times R3 factorial, and so on. So in this case with the Tallahassee example, using this formula, I would say, okay, I have 11 factorial. I have n objects. Okay, I'm looking at all n of them. So I have 11 letters in the word Tallahassee. I'm looking at all 11 of them, and I have R1 like elements of one kind. So what I mean by that is I have 3 elements that are all A's. So down here, I will have to put 3 factorial for my 3 A's. Okay. Then it says R2 like elements of another kind. So I have 2 L's. So I put 2 factorial down there for my 2 L's. I have 2 S's. So I put 2 factorial for my 2 S's. And 2 E's. So I would put 2 factorial for my 2 E's. And you'll say, well, what about the T and the H? Well, I only have 1 T and 1 H. So I could technically put 1 factorial because I have 1 T and 1 factorial for my H. But 1 factorial is just 1. So I don't have to put the 1 factorials there. But to solve a problem, if I have elements that are repeated, or I have R1 like elements of one kind, R2 like elements of another kind, you have to divide out some of those permutations. So in this case, I know that 11 factorial is the same as 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times, and I'm going to write 3 factorial here because I know then there's a 3 factorial on the bottom, and those could cancel. So then I'd have 2 factorial, 2 factorial, 2 factorial. So my 3 factorials can cancel, and so that would be equal to 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4. And I canceled my 3 factorial, so times divided by 2 factorial times 2 factorial times 2 factorial. And 2 factorial, that's really 2 times 1. So it's really over 2 times 1 times 2 times 1 times 2 times 1. And so then I can, divide out my 2's, like I could 2 times 2 times 2, that's 8, so I could get rid of this 8. I could rewrite that as 11 times 10 times 9 times 7 times 6 times 5 times 4 And my answer will be 83,000 or 831,600. Okay, so that'll be the answer when I solve that. You could solve it different ways. You could take this in your calculator and divide it by 2 factorial times 2 factorial times 2 factorial. But all I did was I solved that out and I got 831,600. All right, now, one last example, and this is kind of a unique case. So this is a little bit different than the last one because it says you're making a 3-digit secret code with the 4 digits 1, 3, 5, 7, and any of the digits can be repeated. So this is different than how many different arrangements of the word Tallahassee can you make, because it says any of the digits can be repeated. How many codes are possible? So this means that 555 is a possible code. So if you're doing this, you would have 4 choices for the first digit, but then you would still have 4 choices for the second digit, and you would still have 4 choices for the last digit, because any of these 3 can be repeated. So that would be 4 times 4 times 4, which would be 64 possible codes, because any of them can be repeated. So that's different from Tallahassee. It just says how many arrangements can you make. So if you have elements that are alike and you can't repeat anything, okay, it's different than that problem. But if you're taking all of them and you don't want to have the same, like TLLAHASSEE, you would still get TLLA if you put the first A in the 10th position and the second A in or the first L in the 10th position and the second L in the 9th position, or you took the second L and put in the 10th position and the first L and put in the 9th position. So in that case, you'd have to divide out. All right. So finally, let's do a couple of examples here. How many different ways can 8 children be seated in a row of 5 chairs? So you have 8 and you're taking them 5 at a time. So the easiest way to do this is to take 8 and you're going to pick 5 at a time. So that's 8 permute 5, and that formula says, if you go back to the formula, it's n factorial. So in this case, my n would be 8 factorial over n minus r factorial. So 8 minus 5 is 3 factorial. So this will be equal to 8 times 7 times 6 times 5 times 4 times 3 factorial, and the bottom 3 factorial. So my 3 factorials will cancel, and that will be equal to 8 times 7 times 6 times 5 times 4. Okay. So that is 6,720. Whoops. 20. Okay. So it says how many 5-digit zip codes are there with no repeated digits? So that means you cannot repeat. So I have 5-digit zip codes. 1, 2, 3, 4, 5. So total there are 10 digits. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there are 10 choices for the first digit, and then 9, because it's very clear there are no repeated digits. And then 8, and then 7, and then 6. So in this case, I would have 10 times 9 times 8 times 7 times 6. Okay. Okay, which is 30,240. And this is really the same as 10 permute 5. Okay, I have 10 digits. I'm taking 5 at a time. They're all distinct. So if you go back real quick here in this formula, I highlighted the word distinct. Distinct meaning none of them are repeated, okay? So I have how many 5-digit zip codes can I make? None of the digits are repeated. So 10 permute 5 would still give you the same answer of 30,240. So this says 6 people are in a contest. How many ways can first and second place be awarded? So this would be the same, in this case, as 6. Okay. And I'm going to pick 2 of them. I'm going to pick a first and a second place. Okay. And so if I calculate that out, that would be 6 factorial and over n minus r factorial. So 6 minus 2 would be 4 factorial. So that would be the same as 6 times 5 times 4 factorial over 4 factorial. The 4's would cancel, and that would give me 30. So what I would like you to do is try and finish these 5 problems here using the notes, and let me know if you have any questions. Thank you.